You ever wonder if a machine can learn without a teacher? Without an answer key? Well, today, we're diving into the pretty amazing world of unsupervised learning. This is where algorithms get set loose on data to find hidden patterns completely on their own. Let's dive in and see how it all works. Just picture it for a second. You'd probably start making piles, right? You'd put the round red things over here, the long yellow ones over there, and so on. You're using features like color, shape, and size to create your own groups. And nobody had to tell you, hey, that's an apple or that's a banana. And just like that, you're finding the structure all on your own. So that simple act of sorting fruit, that's actually the core idea behind a huge, huge field in machine learning. Let's take a look at how that intuition gets a little more formal. And that right there is the crucial point. Unlike other methods where you might feed an algorithm pictures of cats that are all neatly labeled cat, here there are no labels. The machine has absolutely no correct outputs to learn from. Its entire job is to just look at the raw stuff and figure out what's similar to what, all by itself. So why would we even do this? Well, for one, creating all those labels can be incredibly tedious and super expensive. Unsupervised learning just skips that whole problem. It lets us find these hidden structures in massive piles of data. We're talking about things like identifying customer groups you never even knew you had, or spotting weird anomalies in financial data. It's an amazing tool for pure discovery. Now, one of the most common jobs in unsupervised learning is something called clustering, which is really just a fancy word for grouping. And when it comes to clustering algorithms, there is an undisputed champion, k-means. Okay, so k-means is by far the most popular clustering algorithm out there. Think of it like a librarian who has a giant, messy pile of untagged books. The librarian decides, I want to sort these onto 5 shelves. That number 5, that's their k. The whole goal is to arrange the books so that every shelf has books that are as similar to each other as possible. That is exactly what k-means does, but with data points. But here's a cool little twist. In the standard version of k-means, every single data point, every book in our library, is treated equally. But with something called weighted k-means, we can actually tell the algorithm that some points are more important than others. This is super useful for dealing with outliers, those really oddball data points that just don't seem to fit, by just giving them a really low weight so they don't mess up the whole grouping process. All right, so we know what it does, but how does it pull off this magic sorting trick? Well, it all comes down to a surprisingly simple 2-step dance. This is it. The whole thing is just 2 simple steps, repeated over and over. First, the assignment step. Every data point looks around and gets assigned to whichever group center is closest. Then, the move centroid step. The center of each of those groups gets recalculated and then moves to the new average spot of all its members. That's the whole dance. Assign, move, until nothing changes anymore. Let's actually watch it happen. On the left, that's our raw, unlabeled data, just a cloud of points. Then, on the right, the algorithm makes its first move. It just randomly plops down 2 cluster centers, or centroids, right into the middle of everything. We've decided we want 2 groups, so our k is 2. This is square 1. And here's where the dance really begins. In step 3, every single one of those green dots is measured, and it gets colored either red or blue depending on which center it's closest to. Then in step 4, you can see the magic. Those X's are centroids. They move. They get pulled right to the average position of their new red and blue team members. You can already see them drifting toward the heart of their clusters. And it just keeps going. Rinse and repeat. The points get reassigned, the centers move again, and the groups get tighter, cleaner, more defined. The whole process keeps iterating until the centroids just stop moving. When the picture in step 5 looks exactly the same after another round, we say the algorithm has converged. It's found its solution, 2 beautiful, distinct clusters. Okay, so grouping dots on a screen is cool and all, but what can you actually do with this? Well, k-means has some seriously powerful real-world uses. Let's look at one you definitely interact with every single day: image compression. So, how in the world does grouping dots help you shrink a photo? K-means can do something called lossy compression. Now, that word lossy might sound bad, but all it really means is we're willing to trade a tiny, tiny bit of the original image quality for a much, much smaller file size. So here's the game plan. A single image can have millions of different colors. Instead of keeping track of every single one, we first pick a small number, k, let's say 64 average colors that we want to use. Then we treat every pixel in that photo like a data point and use k-means to group all the similar colors together. Finally, we go back and replace each pixel's original unique color with the average color of the cluster it ended up in. We just took millions of colors and squashed them down to only 64. And the payoff? It's absolutely staggering. An original image might need 24 bits of information to store the specific color of every single pixel. But with our k-means trick, using 64 colors, we only need a little bit of space for our list of 64 average colors, and then just 6 bits for each pixel to say, hey, use color number 32 from the list. For any decent-sized image, that is a massive savings in file size. Now, as powerful and as cool as k-means is, it's not a silver bullet. It's really important to know that it has some limitations. For one thing, picking the right k, that is, the number of clusters, can be more of an art than a science. If you pick the wrong number, you're going to get weird results. Also, remember how the algorithm starts by placing its centers randomly? Well, that means you can actually get different final clusters if you run the exact same process multiple times. It's not always consistent. And finally, it can be pretty sensitive to the scale of your data, which just means you often need to prep your data a bit to get the best results. But hey, even with those quirks, unsupervised learning is a total cornerstone of modern data science. It lets us find order in chaos. And as we generate more and more data every single day, the real question isn't just what we can do with it, but what incredible new patterns these self-sorting algorithms are going to help us discover next.